Hello, Bill. Still holding the fort, I see.
How are you, George? Haven't seen you around here in a long time.
This is Bill Miller, the chief of our transmitter station. Bill, Mr. Thomas.
Glad to know you, Mr. Miller.
How do you do, Mr. Thomas? It's quite an event for us to have a broadcast from here.
This is a special one on vacuum tubes, Bill. How about showing him some real ones?
Oh, sure thing. Step right over here. Take a look in there, Mr. Thomas.
That's where your voice current is stepped up before it goes out into the ether, Lowell.
It's a whopper, isn't it?
They're among the largest tubes made, Mr. Thomas. They handle so much power that they have to be cooled by a circulating water system.
Yes, sir. If it weren't for these babies, there wouldn't be any radio. And worse yet, Bill and I'd be out of a job.
You bet.
Yes, and a million others owe their jobs to the vacuum tube, including myself. As a matter of fact, practically everybody has been benefited by it in some way. My broadcast begins with 25 years ago in New York, Alexander Graham Bell repeated the first words ever transmitted by telephone. "Mr. Watson, come here, I want you." But this time the inventor's assistant laughed. "I can't make it under a week, Dr. Bell. I'm in San Francisco." It was the first transcontinental telephone conversation. This exchange of greeting marked the opening of transcontinental telephony. The same year saw speech transmitted across the Atlantic by the first radio telephone. Yet both of these miracles of communication developed from a single discovery, the vacuum tube. A discovery which sprung from a chance observation in this workshop of a great inventor at Menlo Park, New Jersey. The story begins in 1883 with trouble, the breaking of the filaments of Thomas A. Edison's incandescent lamp. Observing that the break invariably occurred at the positive end of the filament, Edison reasoned that some unknown negative electrical particles were bombarding this end of the hot wire. Further experiments revealed that the flow of charged particles could be influenced by an extra wire sealed into the bulb of the lamp. Edison recorded this curious phenomenon in his notebook and turned to his many other inventions. It became known as the interesting but useless Edison effect. A generation later, Dr. Lee DeForest added a third element which transformed the Edison effect into a bottle of magic, the first vacuum tube. But it remained for Bell Telephone Laboratories scientists and engineers to perfect and commercialize the vacuum tube. Notable among this host of researchers for Western Electric and the Bell system were Drs. Jewett, Colpitts, Vanderbilt, and the late Dr. Arnold. With their colleagues, they developed the tube into a commercial sensation. And then in 100 specialized forms, they applied it to the facilities of electrical communication. Thus, from this product of the Bell Laboratories grew 4 great new industries: long-distance telephony, radio, the modern phonograph, and the sound motion picture industries. Can you recall the telephone of a generation ago? New York to Denver was the longest call that could be made, and it was uncertain. Then the vacuum tube went into service, and the transcontinental telephone became a reality. Lines spread to every city and town and hamlet in the country. Radio telephones spanned every ocean, connecting the telephone in your home with 38 million of the world's 40 million telephones. All because a vacuum tube can amplify the human voice without distortion. The product of this magic lamp we call a vacuum tube is not light, but electricity. Electrons set free from the atoms of matter that hold them captive. And the world and all it contains are built of atoms. Yet hidden in every single last atom is from 1 to 92 electrons. This wire, like everything else, is composed of atoms. And if microscopes could magnify 10 million times instead of paltry thousands, one of these atoms probably would appear as a tiny elastic sphere, a sphere formed by negatively charged electrons swarming around a massive nucleus of positive electricity. Some substances, especially metals, do not keep their electrons tightly bound to the individual atoms, but allow them to roam around aimlessly between the atoms in the interior of the substance. Such substances are called electrical conductors, because if a battery is connected to the ends of a wire made of such a substance, the free electrons drift along the wire, continuing their aimless motions as they drift. It is this mass movement of electrons that we call an electric current. Whenever the aimless motion of an electron carries it past the surface of the metal into the space outside, it is immediately pulled back by the electric attractions between the electron and the atom community it has left. To become useful in a vacuum tube, however, these electrons must be separated from their atom communities and allowed to move alone. This we do by heating the wire with an electric current. The atoms and electrons become increasingly agitated until some of the electrons rush at the surfaces of the wire at high speed, speed so high they could flash from New York to Detroit in 1 second. At these speeds, electrons are able to break through the electric forces which try to restrain them. They escape to move about in space outside the wire. Now, if we set up a nearby target of positive electricity, the electrons which escape from the surface of the wire are pulled directly to the plate. Actually, however, the space between the wire and plate is jam-packed with gyrating air atoms, literally billions of them. And to reach the plate, the electrons would have to bump their way through them like midgets in a subway crowd. And many of the electrons would be pulled into strange atoms on the way. This problem is solved by enclosing the wire and plate in a glass bulb. Then a vacuum is created by pumping out every possible air atom. And right here is where we get the name vacuum tube. Now the negative electrons shoot straight at the positive plate without interference. This pulling of electrons from atoms isn't done for amusement. On the contrary, it's an important economic problem. Research to date has increased many-fold the number of electrons that can be freed for a cent. And each year, this little item alone saves us about $12 million on power bills to run our radio sets. Here's how it was done. Research revealed that some atoms give up their electrons more willingly than others. So the engineers devised coatings for vacuum tube filaments. These coatings produce surfaces which permit electrons to escape at comparatively low temperatures. In this way, the power required to heat the filament is substantially reduced. Now, with but a trickle of current, the improved filament barely glows. Yet away from each square inch of its hot surface flow more than 10 trillion electrons a second. The positive plate, the tube's second element, is completed by adding an outgoing wire. Control, however, is lacking. Needed is a traffic cop on the electronic highway. And this is the job of the vacuum tube's third element, or electrode, the grid. And with its introduction begins the real utility of the tube. Made negative to repel the negative electrons flowing from the filament, each increase or decrease of voltage applied to it lets few or many electrons pass to the plate. Or should you prefer an Arabian Nights technique, these aroused monkeys throwing pebbles at a target through a shutter ably portray what goes on in a vacuum tube. Simple, isn't it? Yet it's the essence of one of the world's most important discoveries. The ability of the electronic vacuum tube to amplify or control any sort of electrical wave motion puts 100 million new tubes to work each year. Yet if we know how they are used in telephony, we can understand their function in all speech transmission apparatus. To reproduce the human voice across the United States without vacuum tubes and telephone lines would require about 150,000 hog callers spaced within earshot. The time entailed, more than 5 hours. The telephone does it better in 1/12 of a second. And instead of hog callers, It uses repeater stations, 40 or more, dotting the speech highway, for instance, between New York and San Francisco. Inside are banks of vacuum tube amplifiers, repeater tubes, the telephone engineers call them. Tubes in each repeater station function on every long-distance call, amplifying the voice each way. Here's how it's done. Vibrating under the impact of sound waves, the transmitter diaphragm starts a pulsating movement of electrons along the wire. But as the energy of the electrons is gradually used up in forcing those ahead into like pulsations, the voice current becomes weaker by the mile. Entering the grid in feeble waves, the voice current is nevertheless ample to mold the electrons flowing from the filament into a similar wave pattern. Re-energized without distortion, the voice current now speeds from the plate and tube, arriving at the receiver with just the right strength to reproduce the original sound waves. How much is your voice amplified by these repeater stations between New York and San Francisco? You say it, I can't. The figure is 10 with 99 zeros after it. Yet the voice sounds are neither louder nor softer when they arrive than they were when they started. For these magic lamps amplify enough to exactly offset the energy lost on the way. Regardless of the merit of an invention or discovery, it achieves greatness only when it contributes to the well-being of many people. This is the role of Western Electric and like organizations, the mission of making such inventions as the vacuum tube available to all of us. Theirs is the exacting business of building into each product the qualities of long life, dependability, and operating efficiency. Here in the Western Electric vacuum tube plant, each operator is a skilled craftsman, a trained specialist in his or her particular task. This painstaking care in manufacture has earned for the telephone repeater and its sister tubes the unique distinction of being custom made. Typical is the making of repeater tubes, the vacuum tubes used in long-distance telephony. They begin their long life in this automatic hot-cut flare machine. Long lengths of glass tubing are cut into pieces and carefully flared to size at each end, each piece destined for use in the glass foundation of a tube. The prepared flares are here drawn out at one end to receive the spaced lead-in wires. The flares, prepared and formed, are now put on metal supports in which the lead-in wires have been inserted. Then this stem-making machine whirls the glass and metal combination through the carefully spaced and sized jets of burning gas and through automatic pressing jaws. Into an annealer, it last delivers a complete glass foundation or stem. A stem gas-tight, free from strains, with lead-in wires exactly sized and spaced for the mounting of tube electrodes. The uniformity of Western Electric tubes is largely due to the precise work of this automatic grid winding machine. It holds two heavy wires which serve as grid supports, notches them to secure the small grid windings, winds the finer wire in place, then hammers the notches over the windings. Spacings between windings are uniform to a few millionths of an inch, and the operation is concluded without stretching or deforming any of the wires. From rolls of carbon-coated nickel sheet, this carefully guarded punch press turns out halves of plate sections. The plate halves are next fastened together by a sort of metal stitching called staking. The resulting electrode, the plate which catches the electrons in the completed tube, is accurate in its dimensions to a few thousandths of an inch. The vital third element of the vacuum tube, the filament, is begun in annealing and coating machines. Metal ribbon, the core material, is drawn without stretching through heated tunnels and over pulleys and guides until the chemical coating is completely applied. Running with perfect synchronization, this machine cleans the filament ribbons in the heated tube on top and returns them through 3 chemical coating baths. Throughout this entire process, the chemical composition of the coating and the dimensions of the coated filament are controlled to the closest limits. The elements of the tube are its glass foundation, its filament, grid and plate, together with some supporting pieces. and these are all brought together in the assembly position. On accurately machined jigs, they are fitted into each other and securely fastened in place by electric welding. Adjusted for each weld, the welding machine delivers precisely the amount of electrical energy required to make the metals flow together to obtain a secure joint. Completed, the tube structure is accurate within microscopic limits in all its spacings. None of the parts are distorted in the least as a result of the assembly, and yet the finished product is sufficiently rugged to withstand ordinary handling, both during subsequent manufacture and in shipment and use. At this point, the complete assembly is sealed into a glass bulb. The assembly is held in the revolving head of a gas-fired machine. The bulb is put over it, and then the bottom of the bulb is cut away by melting at a point where bulb and stem can be securely fused together. The completed seal-in, as it is called, is gas-tight and free from strains or leaks or other defects. On this automatic exhaust machine, the tube becomes a vacuum tube, for all gases are drawn from it. With vacuum pumps operating full blast, the tube is swept into a tunnel where it is heated electrically to a degree just short of melting the glass. This drives all impurities out of the glass envelope and the tube elements and down into the pumps. At this point, the base is fitted over the lead-in wires. These are clipped and bent into position, and the tube is sent through a gas-fired tunnel to fasten the base to the glass by high-temperature cementing. From the basing machine, the tube goes to the soldering position. Here, the leads are soldered to the sides of the metal projections that make the contacts between the tube elements and the telephone circuit in which it is to be used. Each based and soldered tube now goes into an aging socket and receives full load operating voltages for 8 to 16 hours. And at the end of this stabilizing treatment, it is tested for uniformity, stability, and serviceability. And finally, the repeater tube is carefully cleaned. It is now ready for use. But even here, insistence on manufacturing perfection is manifested in the sample tubes picked at random from the production line for special tests and life runs. And in these files are kept the records of each of these sample tubes, records which show that these tubes will operate over 50,000 hours and still perform at top efficiency. Here are the tubes which give voice to radio and talking pictures, tubes that enable the public address system to speak to thousands and the telephone user to talk across continents. And built into all of them are the endurance and high performance of the telephone repeaters, from those no larger than a peanut to this 100 kilowatt job, and giant 250 kilowatt vacuum tubes, the biggest broadcasting tubes in the world. Yes, tube making in this plant is more than a manufacturing process, it's an art. And the men and women you have seen are artisans, artisans who translate the achievements of research into the qualities inherent in all Western Electric vacuum tubes. A distant earthquake or bringing an elevator level with the floor, wherever you find the vacuum tube working its magic, it will be promoting your security and comfort and convenience.
Calling Flight 14. Okay, 14. Weather at terminal, ceiling unlimited. Thin scattered clouds at 500 feet. Visibility 5 miles. Wind northeast 17 miles.
There is only one course, and that course begins with a decision that the rights of man, liberty, and justice are in the United States to stay.
Hello, Mother. I'm phoning from the ship. We're 1,000 miles at sea.
Okay, headquarters. Car 60 on the way to Lee Avenue, call.
Get me a radio compass bearing on that SOS. Hurry it up.
All of these things and more are happening every day, happening because of a single product of industrial research. And while it was girdling the earth with speech, the vacuum tube added billions to our national income, raised our standard of living, produced numberless new conveniences. From it developed great and small new industries, the network of long-distance telephony, radio broadcasting, high-fidelity recorded music, talking motion pictures. This magic lamp has created 1 million jobs in every city and town and village in the country. Jobs in service and manufacture, jobs in entertainment and education. It has built 1,000 factories, opened 10,000 stores and shops, created vast demands for the raw materials of farms and mines and forests. All these things and more happened because of a single product of individual enterprise and the American way of life. And so long as they endure, there will be no end to the miracles of this modern Aladdin's lamp, the vacuum tube.